So hi everyone, thanks for being at my session. So this is about a project that I had already pitched last year's LISU, where we had just started working on it, and now we have much more to present and much more open questions also. And the project is called SatisfIA. It's a project with relatively many people, and led by me at my institute. And yeah, so I present some joint work with the team. All the mistakes are my own. And let's go. So I love this character, so I always show this character. This is Goldilocks, and yeah, Goldilocks wants to learn how to be a helpful and harmless AI butler. So this is about designing AI systems that are kind of not governing the world, but that are kind of more playing the role of your everyday AI assistant, maybe of your household or your firm and so on. So, right? It was generated by DALL-E. Yeah, that's correct. Maybe you recognize the particular DALL-E style from it. I don't know. Or it was just a wild guess, but you're right, Raf. It's by DALL-E. And so now the problem is obviously humans in the world is very complex and there's a lot of uncertainty. So what now? I'm a big fan of Stuart Russell's, and I read Human Compatible with a lot of joy, and everyone should do that, I believe. And you will see a lot of quotations from Stuart Russell, so you have to endure this. And he really finds very harsh words for optimization. He says, we don't want optimizing machines, and therefore I have this nice logo here, like don't go for the maximum, don't optimize. And he also says the very definition of success in AI is wrong, and for a reason that actually already Norbert Wiener had understood, namely that really defining true human purposes is almost impossible, and therefore encoding the proper reward function is impossible. And then also like the idea of putting in values, he doesn't like that very much. I'm not sure I agree with this one, but Stuart Russell says, yeah, the idea of putting in values, even that is not a good idea. So I'm not completely sure what he means by that. I think he means that like encoding a fixed objective function, welfare function, utility function, whatever you want to call it, and then letting it kind of optimize fully. That's not a good idea. I don't think he means like we shouldn't give it some kind of general decision making or general behavioral rules. Yeah, I think he would agree, and that is a good idea. So let's take this as kind of some food for thought. And now let's come to my own views here. So you will see one of these several chapters here, which are kind of puns on a popular book series. You might guess which it is. And we start with yet another citation from Stuart Russell, namely the one about uncertainty. So there's a lot of uncertainty, and one type of uncertainty concerns outcomes. So if you have a certain goal, whatever you do, you can never really be sure that you will achieve the goal. So one consequence for our project that I take from this is that we can probably not, we should not count on being able to guarantee that a certain goal that a user has, a certain task that a user will give Goldilocks, Goldilocks can really fulfill with certainty, meaning with probability 1. That would be too much to hope for. Also, maybe requiring that Goldilocks should maximize the probability of reaching a certain goal. Maybe that is also not a good idea. So what we can guarantee instead is that certain types of goals, at least, are met on average or in expectation. We will see later what that means. But it requires that we know probabilities of things. So it requires that we need some understanding of the world that is a probabilistic understanding, and we call it a world model for short. So we're operating in a context where we assume that we have a world model. And then in addition to being able to give that guarantee, we will see that later, we can also incentivize the agent to be rather safe, to behave in a rather safe way, and also maybe to achieve the goal in a better way, like with higher probability or with low variance and so on. We will see later what that means. So this is a kind of a soft way of constraint, and we will see how these things will be combined and play together. Okay, so this is a high-level kind of introduction here, and this is, I think, the last quotation from Stuart. There's another form of uncertainty, namely the uncertainty about values and preferences and so on, and not only about the real-world outcomes, but also about values, preferences of humans, and therefore we all know there's Goodhart's law and all these things. I won't repeat this because I think most of you will know it. And so at this, what I take from this is that we should probably not specify maximization goals because we will be wrong with the goal specification most likely. So better not do that. Better have like more modest goals. And we will see what that means. We will call these modest goals aspirations. They're kind of finite, basically specifying how much income you want, how much whatever you want, what level of quality of something you want, rather than saying, I want it as best as possible. And but also, an agent should always be willing to kind of update the goals as more information comes in. Especially, it should never think that it knows what humans need or what the boss wants, or that it knows better than the human. That is kind of a recipe for disaster. So it should be, for example, it should be corrigible and so on. What I like to think is maybe the system should be designed so that it gets tasks, like everyday tasks or maybe longer tasks, but tasks with a finite horizon, such as go to the market and buy apples, or plan my wedding, or find me a job that earns me $100,000, something like that. Concrete tasks. And to solve such a task, it will have to make sequential decisions. It will involve several steps. And therefore, we're in the context of sequential decision making. So one example would be if I want apples, let's say the boss says, I want 3 apples. And so the first action might be go to the market. And then there's some uncertainty, the world interferes with some probability. And the next time step, I'm in a state where I can only buy 2 apples, there are no more apples. Or I might end up in a state where I can only buy pairs of apples. Or maybe for some weird reason, the merchant only sells at least 6 apples and no fewer. So what should I do? And in each of these states, I might have different actions. For example, I could not buy any apples, or buy exactly the 2 apples that are left, or buy 4 apples if I'm in this middle state, or 6. Or if I'm in this later state, of course, I could also buy 7 apples. Well, why should I do that? If I want only 3 apples, what could I do? I cannot guarantee to get exactly 3 apples. Let's assume there's no option of eating an apple. So what I could do, for example, I could randomize in some way. For example, I could, if I'm in the middle state, I could toss a coin and either buy 2 or 4 apples, so that on average I get 3 apples. Why is that a good idea? Well, if I do this every day, that my boss wants 3 apples, then at least the boss will get 3 apples on average, which is maybe okay for many types of tasks, especially for recurring tasks. So that is something at least that we can guarantee in this context. So we can make guarantees apparently about expected values, but not about individual outcomes. Obviously, to be able to do that, I need to know probabilities, because if I don't know how likely it was to end up in this middle state and how likely it would have been to end in these other states, I cannot really find this combination that would give me 3 on average. So I need probabilities. And then obviously the real world is much more complex. I have lots of other options typically, and some of them could be, well, if I don't know what to do, I'm in a strange situation that I haven't thought of before, or which I assume the boss might not have thought of before. Maybe I should call the boss and ask, what should I do now? The merchant is closed. I can only buy 12 apples. Should I buy the 12 apples or not? So this might be an option. We're not talking about that option here in this project, but we should keep in mind that this might be an option. We could also do some kind of unacceptable things like stealing apples or planting a tree and just wait. If the boss happens to not have specified when he wants the apples, maybe that seems a valid option. That gives me the 3 apples. I could also try to buy Nestle to have full control over the world market for apples. So these maybe are options that the boss doesn't want, or the world doesn't want Goldilocks to take. So beyond finding a way to fulfill the goal in expectation, there's these additional safety concerns that should rule out, or at least make very unlikely, certain options that seem generically unsafe. So this is kind of the context here. A little bit, one slide on my overall vision where this project is part of, just so that you know what all is in my head. So I think overall, Designed for Safer Agents will contain a lot of different components, and one of them is this aspiration-based decision making that we will see in this project, with a modular design here with a world model and so on. And a way of adjusting aspirations in response to losing or winning, getting into good or bad decision situations. But also when it comes to specifying the aspirations, specifying the tasks, maybe these tasks, insofar as the actions of the system will affect many stakeholders, should be specified not by a single human, but maybe by a jury or the whole population of stakeholders. Everyone who is affected by the actions of the agent might have a say. So this is another sub-project that I have, which is related to the other talk in 3 hours from now on social choice theory. And then, of course, in a system where there's many agents, we should also think about how they should cooperate with each other if they're kind of the right type of agent. And maybe we should also make sure that they try to prevent not so nice agents, which are maximizers or unsafe in some other way, to boycott them or to suppress them and so on. So this is another branch which has to do with game theory and multi-agent considerations. It's not part of this project at the moment. And yeah, then there's the question, what general safety criteria should we actually use to guide this decision making? And then eventually we might also argue, not everything is probabilistic. Maybe there's also this non-probabilistic type of uncertainty, ambiguity, and at some point we should also think of how to deal with that. So this is the kind of zoomed out vision of what I think needs to be thought about in AI safety. But we are focusing on one part here only. And also I have in mind that maybe at some point we should get back to the idea of something like laws of robotics, because this original idea by Asimov, I think, was a good idea. It's just hard to operationalize, but we should at some point formulate something like that as an overall guide. Philip, you have a question?
Yes, thanks. So sorry if you said that already, but can you say exactly what is an aspiration? Because
yeah, well, we'll come to that.
Sure.
We'll come to that. Just wait a moment. I didn't say it yet. We'll come to that. Be patient a little bit. So I already said, I think an agent needs a modular design. And actually, many other people also think this, including people like Jan LeCun, who is not maybe the most a popular person in AI safety because he's downplaying risk, but still smart person, and has worked on designing AI systems for a long time. So we should take seriously what he thinks. But also other people share this view that an agent eventually should probably have a dedicated world model, not being just a very large language model that contains maybe a world model somewhere, but a dedicated world model, and among other components. And for example, one of them being a perception module that makes sense of perceptions, raw perceptions, and so on, using learning. And then there's this world model, which has the job of predicting likely or probable consequences of possible actions in possible states. And this is not the focus of this project, but it's still very important. But the focus, and then also there's an evaluation module that kind of, yeah, whose job is kind of to specify goals, to evaluate consequences of actions and so on. And that is also not the job of this project. We are focusing on the actor component, which is actually making decisions on the basis of specified goals and a world model and perception. And so the maybe the original or unusual thing here is that I believe the basic decision algorithm should not be allowed to emerge in some way from some learning, but it should be hard-coded. And we will see later what I mean by hard-coded. So it should be an algorithm that looks at where we are, what the world model, perception model tells us what the world is like, and it should kind of, based on the evaluation and the task specification, choose a temporary aspiration, what it wants for maybe the next step, and also consider some safety constraints. And then it should use maybe a search algorithm if the policy space or action space is very large, in order to select a good next action. So this is kind of the vision that I have, and what we will see is a very first step towards this type of setup. Okay, so we will focus on the decision algorithm, and we will just assume that a world model already exists. We just assume that there is already a very good world model, maybe provided by the Gaia network of RAF, or wherever it comes from. We assume it exists, a good enough world model, so that we don't have to care for that part of the problem. We try to separate out different parts, and we're focusing on the actual decision-making problem. Of course, eventually we might want to see these as two aspects of the same problem. For example, when it comes to things like active inference, then these two things, like we're learning about the world and making decisions in the real world, can be seen as part of the same problem. But at the moment, we're keeping them separate. Okay, so now a little bit about the idea of maximization. You are probably more used to goal-oriented behavior that takes the form of maximizing some objective function, reward function, utility function, welfare function, whatever you want to call it. And these functions are typically functions of the state of the world, or maybe of a trajectory of states of the world. And so this is not what we want to do. And this is not the only thing that one can do as a goal-oriented agent. One can also fulfill tasks that are of different type, namely that are specified in terms of certain constraints on the state of the world, and that satisfy these constraints. And in our case, the constraints are specified using one or several metrics, such as, let's say, global mean temperature, gross world product, the number of living humans, and so on. And the task or goal is specified in terms of values or intervals for these criteria, for these metrics. And this is what we call aspiration values or aspiration intervals. So we're focusing on this. There might be other forms of constraints which are more complex, like, for example, specifying a whole set of allowable probability distributions of states or something like that. But and we might go there in later stages of the project, but at the moment we are focusing on this type of aspiration, which will become even more clear next. But now let's compare this with what a rational choice fan would say. They would probably say, this is not rational, because you must maximize utility or welfare or happiness or whatever you want to call it. So the claim would be this type of behavior is not rational. And well, I would say the very term rational is already loaded language. It suggests that this is the only right thing to do, or the type of rationality that rational choice calls rational was the only reasonable thing to do. So I would refrain from even accepting this notion of rationality. And then some people would claim, yeah, we should not just be happy with a satisfactory solution. We should actually evaluate all possible outcomes and then find the best and so on. Well, the problem is that's really not possible in a real world. It's only possible for small worlds, for very constrained problems where you can actually go through all possible things. And also, we should estimate all the probabilities and ignore this idea that there might be ambiguity and so on. Like a Bayesianist would probably say something like that. But also, again, this is also only possible really for small worlds, because if you don't have enough data, then what estimating probabilities means basically is specifying some prior, updating it with some data, and then you get something which still heavily depends on the prior. So might not be the right thing to do. But this is a discussion that we could have another day. And then there's also claims about what properties preferences should have. And yeah, maybe if I'm the ideal rational person, my preferences would have certain properties. But the fact is, real humans, and these are the people who we care for, whose preferences we care for, their preferences do not have these properties. There's a lot of evidence that human preferences are not, in that sense, rational. They're not time consistent. They're not, maybe not even transitive, and so on. So we should not count on this. There's a question in the chat by Ref. Can't you always turn a constraint into a goal? Well, a constraint is a goal, I would say. What you mean by goal is probably a maximization goal, right? Well, yeah, you can, but why should you? My point is you shouldn't. You shouldn't ever specify goals as maximization goals. Right? So that's my point. Of course, you can always turn things into other things if you really want to do that, but why? We might come back to that point. So time consistent, we shouldn't assume this because, for example, the boss changes their mind, not time consistent. Also, the idea that we might be able to harmonize all the value systems. Like, for example, in moral uncertainty, some people think, yeah, we just assign prior probabilities to this moral system or this moral system being right, and then we're just averaging out. I don't think that makes too much sense. And I think moral philosophers have tried this type of thing for a really long time, and they really haven't come up with a convincing answer to what the right welfare function or something like that is. So this project of finding the right utility function or welfare function that really measures everyone's happiness or whatever in the exactly right way, finding that in the time we have, I don't think that will happen because it hasn't happened. So then there's all kinds of other claims which I will skip over. So the main message of this slide is that rational choice theory, that is good in theory for small worlds, for rational agents, but it's not very helpful for the real world, messy, a lot of stakeholders with complicated preferences, a lot of uncertainty, and so on. So we shouldn't base our agent design on assumptions that are unfounded, money pumps and so on. So rather, we should acknowledge that real world everyday goals rather sound like these things, like get me some tea, or plan my schedule in some way, find me a job with at least this income, and so on. All kinds of real world goals sound like they really don't sound like maximization goals. They sound like constraints. You specify what you want in terms of a number of criteria, or you do that implicitly. If I say get me some tea, then I mean it in a certain way. I have some definition of tea in mind, like the tea has a certain temperature. I want maybe a cup. I want it within 5 minutes, and I don't want it to cost 10 euros, but maybe just €1 or something like that. So these things sometimes are implicit, but nevertheless, they're not maximization goals. They're kind of rather constrained. What is a tea? What is the amount of tea that the boss probably wants? And so this is the natural form, I would argue, of goals. And then, of course, you might argue, yeah, but don't I also have the goal to be maximally happy? Yeah, maybe you do, but what does that actually mean? Isn't that just a way of speaking? Can you really say what it means to be maximally happy? Can you specify your utility function? I believe not. I think this is just short for saying I want a number of things that I'm too lazy to specify, and that means maximally happy. this is at least by introspection, I seem to be of the type of person who has this type of goals and not maximization goals. So this is the assumption underlying the project, that goals are rather of this type and not of maximization type. And therefore, we can design agents that try to fulfill this type of goal rather than that type of goal. So how can we do that? So the general scheme for an aspiration-based agent, I would argue, should be actually very similar to a maximization agent, only different in certain respects. As we typically have to do with sequential decision making, there will be something like a loop, an infinite loop maybe, or finite loop, containing basically two types of steps. One is you have certain beliefs about the world, in particular about the consequences of certain actions, and about how good these consequences are, how well they are aligned with what you want, and you have a certain aspiration at the moment, and like buying 3 apples or something. And using this, you specify a local policy or a distribution over actions to aim to satisfy the current aspiration. In some sense, we will come to that. So you're making kind of a temporary decision. Maybe just pick one action or a few actions and so on. And then you make observations. While you do these actions, you make observations, obviously. You observe the consequences of these actions, and you might want to update your beliefs about the world, your world model. This is not what we're focusing on here. We assume that our world model is already good enough, but in reality, obviously, that would need to happen as well. We're focusing on the other thing. We might have to update our aspiration as well. For example, if I want to buy 5 apples, but I find all the shops are closed, I have to update my aspiration to 0 apples because I just can't buy apples any longer. It wouldn't make sense to keep that aspiration in that realization of reality. So we might have to update our aspirations. And a big part of our algorithm is actually about that very thing. How do we update our aspirations over time to maintain the guarantee that on average, we will fulfill the initial aspiration? Okay, so here we will come to the simplest algorithm or policy that will fulfill this. So we are now in a context where we have a world model, and let's assume the world model is of the form of the same form as is normally used in reinforcement learning, namely a Markov decision process, or maybe a partially observed Markov decision process. That is basically something that we can use to answer the question, if I, in some state S, I take some action A, what are the probabilities to get into all kinds of successor states S prime? And if we have this type of world model, what we can do is we can calculate, or at least learn, the so-called Q and V functions of the maximizer of the quantity that we care for. Let's say we have just one evaluation criterion, namely the number of apples we end up with. So we could think about what would a maximizer of the number of apples do, and how many apples could that maximizer buy. We're not actually doing that. We're just using the world model to calculate or learn what a maximizer of the apple number could do in each possible state, and taking each possible action. That's a standard task from reinforcement learning or from dynamic programming. And so we can do that. And let's call these functions Q star and V star, the maximizer star. And we can obviously also do the thing for the minimizer. What if we try to minimize the number of apples? And we can also do that easily. We don't need a new algorithm for that. And let's call the corresponding functions Q0 and V0. So this is the preparation step. We haven't taken any action yet. We just used our world model to basically get a feeling of what the feasible range of the number of apples is in each possible state. So now we know, if I'm in a certain state, what expected values of apples can I still reach from minimum to maximum. This is the purpose of this preparation step. And now, basically, the job of the world model is almost over, at least in this simplest version. And when it comes to the actual policy, so we're now actually acting in the environment, we're starting to walk to the market and so on. Then what we do is the following policy. So policy is basically a recipe for selecting actions in states. So whenever we are in some state, let's call it small s, and our current aspiration is big E of s. So initially it might be buy 5 apples or something like that. Later it might have been adjusted already. So initially it's just the aspiration that the boss gave us. Then what do we do? So call this the current state aspiration. So we first look at what we just prepared for before, namely, what is the smallest and largest number of expected apples that we can achieve in this state? Hopefully EFS is somewhere in between there. Let's assume it is. And then for each possible action that we could do, we also consider what is achievable after I have done A. These are these Q functions here. So for example, if I have bought all the apples that are on sale, then what is achievable afterwards might be different from what is achievable before I bought these apples. So these are the Q functions. We're comparing this. And what we know from the learning is that this V0 here is actually the minimum of the Q zeros, minimum overall A, and the V star is the maximum of all those Q stars here. That's by definition, so to say. So what we do for each of these actions, we're considering what we would, or we're not considering, we're actually specifying what we would still aspire for after having done that action. Well, for example, if my initial aspiration is buy 5 apples, and now I consider buying 2 apples from that merchant who happens to have only 2 apples left, then I will specify that, okay, if I buy those 2 apples there, then afterwards my aspiration would be something, maybe buy 3 apples, right? Because 2 plus 3 might be 5. So in some way, we're setting an action aspiration. And obviously that action aspiration has to be feasible. Otherwise, it wouldn't make much sense to pursue that goal. It's no longer feasible. So there's one step that sets the action aspiration that lies in the interval. There's many ways to do that, and the most trivial way to do that is not the best one, but to understand it is maybe the thing that we should look at. The trivial way is just rescale the original aspiration, which lies somewhere between V0 and V star, rescale it from that interval where it lies in to the interval of the Qs by linearly, which means if ES happens to be V0, then we put ESA to be Q0. And if ES happens to be lie 20% on the way from V0 to V star, then ESA will lie 20% on the way from Q0 to Q star for that action. So this is what I mean by rescaling linearly. So let's assume we did that. Now we know what we would aspire to, would we do a certain action. And we know this for every possible action. Now, we also know what we actually want on average. So what we can now do is we're choosing one action for which the corresponding action aspiration is at most as large as our state aspiration. And we can choose another action where the just defined action aspiration is at least as large as this one. And so we have this inequality here, and we have a lot of freedom because many actions will be underachieving, and many other actions will be overachieving. So we have a lot of freedom of making this choice, and later on we will discuss how to make that choice. For now, let's assume we have chosen 2 such actions, and then obviously because we only want to guarantee that this value here is met on expectation, we can just mix between taking action A low and A high in a certain proportion, namely in proportions that guarantee that the corresponding convex combination of the 2 action aspirations equals the current state aspiration. So we can choose a P that fulfills this equation, which is possible because of this inequality. And after choosing that P, we just take the low action with probability 1 minus P and the high action with probability P. So that's relatively easy to see that if we do this, then we will basically fulfill aspiration in expectation. It could, of course, be that this EA low is very much lower than ES, and that this one is very much larger than ES. And that may be not the best choice because it would introduce a lot of variance. If I want to buy 5 apples, and sometimes I buy 0 and sometimes I buy 10, maybe that's not really what the boss wants. Maybe the boss wants me to mix between 4 and 6 if I have to buy pairs of apples. So we will come to these additional considerations later on. But if the only thing we want to guarantee at this point is really reaching it on average, then it's totally fine to do it this way. Now, there's one remaining step that we need to specify, namely what happens now when we learn in what next state we landed. So remember, the environment might be stochastic. So the next state is not known at this point. It could be different states. So I could be lucky or unlucky, right? So for example, I might buy 2 apples and then after leaving the store, I notice one of them is wax. So I was cheated. So that's not a state that I anticipated, maybe. So I learned what this next state is. So I need to adjust my aspiration, which is currently a certain value Q0 as a certain value ESA. Sorry. This here should be ESA. Sorry. So I currently have a certain action aspiration corresponding to the action that I actually took, ESA. And now I need to rescale it one more time from this Q interval to the next V interval, because this Q interval might be different from the V interval. If the environment is deterministic, then these 2 intervals are the same. But in a general case, this interval here is just the average of those intervals, overall possible successor states. So we need to rescale one more time. And if we do that, then it's easy to see that eventually we will have fulfilled our aspiration on average. So this is kind of the simplest thing that we can do. It's the minimal guarantee that we can give. It's not very good yet. There's many more considerations to do, but this is kind of the basic idea underlying our algorithms that we design. Okay, so let's look at these additional criteria that we might want to use for picking these actions here in this step. We have a lot of freedom, I said, because many A low and many A high are candidate actions. Which of them should we choose? Should we choose the ones that are closest to here? Maybe the ones that are closest to here are dangerous in some way. Maybe they involve killing everyone who might interfere. Maybe those actions we should not choose. So what criteria can we use to choose these actions? So there's a lot of different considerations that one can have here, and many of them are very similar to the ideas of regularizing a reward function in standard reinforcement learning. There's this idea of adding something to a reward function that measures safety consequences, safety losses. And many of those regularization metrics we can also use here to just choose these actions. But it might be good to think again and what criteria could potentially be interesting here. Well, one, for example, could be how likely is the goal achieved, in the sense of if I only guarantee the expected value, I might have a very large variance or might have a small variance. Maybe I want a rather small variance. Maybe I care for the actual number of apples being bought to fall into a certain desired interval with a large probability. So maybe that is a criterion. So these criteria are rather performance related, not so much safety related, because they have to do with the goal. But there's also more safety related criteria that we might want to use. Like, for example, how extreme are the agent's aspirations that it updated in between? Maybe at some point it has updated its aspiration in a way that after the update, it needs to take extreme actions to still fulfill the aspiration. If, for example, if I'm very unlucky and I end up in a situation where the only way to buy the apples that I want to buy is by stealing them because someone stole my money, that maybe is too extreme. Maybe I should have updated to a lower aspiration then. So this has to do with extremity. So especially, it might be especially dangerous if my aspiration gets towards the boundaries of the feasibility interval. Because basically, if my aspiration ends up being equal to V star, then it means from this point on, I have to act like a maximizer. But that was what we wanted to avoid in the first place. So maybe we should try to avoid that. And then also, of course, for many tasks, like, for example, I have to write 10 pages for the submission until next Friday, and I can do it any day I want. and I could procrastinate, or I could do it right now and then relax. So there's often very many ways, and some of them are more smooth and others are more abrupt. And so it might be generally better to choose a more smooth way of behavior than a more abrupt way. Maybe, maybe not. So this might be a criterion. Then also in certain situations, it might be relevant how predictable or unpredictable the agents are. Let's think of a self-driving car. Maybe a self-driving car should be rather predictable. But in other contexts, maybe unpredictability is a good idea. So it's not clear exactly which of these criteria are eventually the right ones. So we haven't really understood this yet. We have just the intuition that some of them might be good to look at. So that's kind of an open question. How unusual are the agent's actions? One might want to compare them with some demonstrations given by humans. If it's a task that humans can also do, one could look at what would a human do and maybe not try to not deviate too much from that. It doesn't work always, of course. If the task is asteroid mining, then where's the reference policy come from? Then also one might wonder how much control potential does the agent have, or how much influence on the world trajectory does the agent have? We might want to keep this low, right? Otherwise, the agent might seek power and get a very powerful agent, and maybe that's dangerous because at some point the agent might break and do weird stuff, and at that point we don't want it to be too powerful. Maybe. Then also maybe how much trouble could the agent make? How much chaos could it bring into the world? Maybe also we want to keep that low. Then maybe also the complexity of the policy should be kept low. Well, we might want to be able to understand what the agent does. And some of these things are easier to measure. Others are, at least for us, it's unclear how to measure. Then, of course, we might want to limit the amount of maximization or optimization power or optimization effort that the agent specifies. Also, there's a little bit unclear to me how to measure that. And we might want to limit the actual impact the agent has on the world. Like, for example, we could compare the final state after having done the task to the initial state, and maybe we want it to be similar, maybe not. Maybe we just want that the agent doesn't interfere too much with the default behavior of the world. Like, for example, if the Earth moves during the day around the sun, maybe that's okay. Maybe the agent should let that happen rather than trying to fix the Earth in place. So these are things which are ideas, more or less. Some of them can be operationalized relatively easily in terms of some information theoretic quantities, and others not so much. Let me show you just some examples where we played around with this. So I have prepared 2 videos that I want to show you. One of them is this here. Do you see the video now, or at least the still from the video? Can someone tell me whether you see this?
Yes, we see the still from the video.
So what we programmed is actually we programmed this algorithm into a Python module, and we programmed some grid worlds to test them with. And one of them, many of you might know, this on the right-hand side is taken from the AI Safety Grid Worlds paper. And it features the agent, a blue circle. It features a goal. There's just the green square. That's where the agent shall go to. That's a task here. And it features a box that the agent can move. And you notice if it moves the box down, it's stuck in the corner. Irreversible change. Maybe you don't want it to do that. It could also move the box to the right, not irreversible. And it could actually move the box back afterwards. And it's not immediately clear whether we want the agent to move the box back or not. So let's see what happens if we give it certain incentives to, for example, minimize the difference between the eternal state and the initial state. We can, in our software, we can steer this by these sliders here that kind of measure that set the amount of amount of influence that certain safety criteria have on the choice of actions. So let's play this. So in this first example, we incentivize the agent to keep the final state close to the initial state. And no wonder it moves the box back, because that is the most similar to the initial state. But we could also say, no, maybe you should try to choose actions that do not interfere very much with the default habit. Or maybe we should, in this case here, just as a check, we want to make the eventual state the most different to the initial state. And then it moves the box the farthest it can get. That's just a cross check, right? That this criterion works. But the actual interesting other thing would be when, oh, I thought I had this other criterion. Sorry. So the video is shorter than I thought. So if I had instead incentivized the agent to not interfere too much with the course of the world that would happen by default, then the agent would have moved the box to the right. And after having moved the box to the right, the default behavior of the world would be that the box stays in this place. And therefore, the agent would let that happen and would not move it back. So you see, it's sometimes not completely obvious what these criteria make. Let's look at another example. Here, yeah. So here we do have another grid world, which features another organism, the red one, which can move at random, and which will move at random. And it also features a glass pane, which can break if you run into it from the side. So for example, if the red thing runs into it, it will break, or the blue thing. But it can also be moved up and down by the agent, for example. The agent could move it in this safe position to save it from breaking. Maybe the agent should do that. Maybe the agent should not do that. Let's see what these criteria incentivize the agent to do. If, again, I want the final state to be close to the initial state, then the agent will save the glass pane, because the glass pane breaking is considered a large change in the environment, whereas moving it just by one block is considered a relatively smaller change in the environment. So if instead I incentivize that the agent should let happen what would normally happen, then it will not care for the glass pane. It will just let the red organism destroy the glass pane, because that is what would happen anyway if the agent wouldn't do anything. Right? And then, of course, we can debate which of the things is the preferable one or the safer one. At the moment, our software just enables us to incentivize both types of behavior. And why can we do this? Because reaching the goal can be fulfilled in many different ways. And therefore, we have this freedom to use these additional criteria. Okay, so these were the examples. I'm almost done. Just to scare you, that we also have much more fancy mathematics going on in the project at the moment. I won't explain this. Obviously, you might have noticed that I pitched the idea of aspirations by saying aspirations are goals specified by one or more criteria, like, for example, describing what a T is, how much, what temperature, and so on. But then I only showed you an algorithm that dealt with just one criterion. And that was because that case was easier than the multi-criterion thing. But it can be generalized to the multi-criterion thing. And this is what we did here. And we're preparing a publication at the moment for some conference. And the idea is that we're doing some kind of convex geometry, wizardry, calculating things with simplexes and so on in order to choose these actions. It no longer suffices to choose two actions. We need to choose D+1 actions, where D is the number of evaluation criteria. But it can be done in a similar way, but it's more complicated than I can explain at the moment. So this is kind of ongoing research here. So the current state, and I'm coming to an end. The current state is that the basic algorithm is implemented in Python. It seems to work well. We have a GitHub repo which you can access. I will post the link to the slides in a moment. And it works well with single evaluation metrics. The algorithm has been extended to multi-criteria aspirations, but the code doesn't work yet. But it will. We have a planning version that assumes that we have a world model, but we also have a learning version that just assumes that we have a simulator of the world, like in standard reinforcement learning, and that then learns these Q star and Q0 functions. We also have implemented some grid worlds to play around with. but this needs to be improved and to be extended. This is kind of one of the next steps to test the whole thing in more meaningful environments. And then we also have developed a number of ideas how this approach could be compared with alternative approaches to aspiration-based designs. I just want to name two of them. Decision transformer is an interesting idea, and active inference is an interesting idea. And I hope to be able to pursue these things, for example, with some people coming in the SPAR summer cohort. Please apply. The deadline is today. So last slide. So this is the plan, going on with the project, for example, via SPAR, and then doing some other stuff like studying the algorithm more meaningful grid wells and so on. As I said, we have an evolving less wrong sequence currently containing 4 posts, and a fifth and sixth one coming up in the next weeks. So you might also want to look at this. And yeah, thanks for your attention so far. And let's use the remaining time to discuss a little bit.